In this video, I'm going to be going over how to write the equilibrium expression for dissolving a solid into water. So if we have our two beakers from the previous video, in one beaker, we are going to dissolve sodium chloride into water. In our second beaker, we're going to dissolve lead chloride into water. Now, from the previous video, we saw that sodium chloride was completely soluble in water, which will break up into sodium plus and Cl minus. So if we want to write an expression for this reaction, we can write sodium chloride solid goes to sodium plus aqueous plus Cl minus aqueous. However, what we need to realize for this reaction is that sodium chloride solid is going to be completely soluble. So when we put it into water, none of that sodium chloride solid is going to exist. So because of that, when we write a reaction for a solid dissolving in water, we will not write an equilibrium expression for a species that is completely soluble. So we would not write an equilibrium expression for this reaction because sodium chloride or any other soluble solid that we're going to dissolve in water is going to completely dissolve. So we will not write an expression for that reaction. Now, if we are met with lead chloride, which is insoluble or slightly soluble, let's see how that will change. So we know that the lead chloride will float to the bottom of this beaker, and a little bit, a very small amount of lead 2 plus and Cl minus aqueous is going to dissolve into this beaker. So what we can do is write an equilibrium expression for this reaction because this is an insoluble or only slightly soluble species. So what we can do is write PbCl2 solid is an equilibrium with Pb2 plus aqueous plus Cl minus aqueous. Now we need to make sure that this equation is balanced, and there are two chlorines over here. So let's put a 2 in front to balance this equation. Now, this is a valid equilibrium expression because when we dissolve this into the beaker, there is going to be some lead chloride solid, or I should say most of our lead chloride will be in the solid form. However, we will also see some of the ions dissolve as well. Remember, when you have a completely soluble species, you do not write an equilibrium expression for this reaction because the solid will completely dissolve and make our ion products. So what do we do when we write our equilibrium expression? Just like any other reaction we have covered in this course, we will write a K expression for this reaction. So what we can see is K is always products over reactants. So our products are concentration of lead times the concentration of Cl minus squared. Remember to put the coefficient as the exponent. Now, this K, similar to how we saw acid-base equilibrium expressions have a special name, this has a special name as well. This is KSP. Now, what does SP stand for? This is the solubility product constant. So SP stands for solubility product, and K is our equilibrium constant. So why is this the solubility product constant? Well, what we are saying with this expression is when we dissolve something that is slightly soluble into water, we want to know how soluble or how much of these ions we will see dissolve into this beaker at equilibrium. So when we multiply hence the word product, our lead and our chloride ions together, or I should say the concentration of those two ions at equilibrium together, this will give us a value for KSP. Now, the higher the KSP means that whatever solid we are dissolving in this water is going to make more products. And if we make more products, that would give us a higher KSP value when we multiply their concentrations at equilibrium together. So a higher KSP value is associated with a solid that is more soluble in water. Now, remember, an overall summary for this video is that a completely soluble species, when it is dissolved into water, is going to completely dissolve. So we do not need to worry about writing a KSP for a species that is completely soluble, because it would be all products. So the KSP for NaCl would simply be sodium and chloride. However, it would only be sodium and chloride, and you would not see any of that solid in that beaker. So when we have something that is slightly soluble or insoluble, like lead chloride, you can write an equilibrium expression to express your solid and your two aqueous ions in equilibrium, and to write the KSP, which is the solubility product constant. You can simply write products over reactants, and we would not include PbCl2 in our KSP expression because it is a solid. So in the upcoming videos, I'm going to show how KSP will help us solve problems that have to do with solubility.